So today's class is about the arrangement of electrons in atoms. We also call this as electronic configuration. In previous classes, we have studied uh, some some detail about electrons in atoms. We have studied how to fill electrons according to the O levels concept, and that concept is not wrong, but it is a slightly simple concept. We also have studied that the electrons in the first shell, maximum electron in the first shell can be 2. In the second shell, it can be 8. In the third shell, it is 32. 18, and then fourth shell, it is 32. So 2, 8, 18, and 32 are the maximum number of electrons that can be accommodated in a shell, in an orbit. And now this shell or orbit is called principal quantum number. Principal quantum number is the number or the name given to shell number or orbit number. But in A levels, you will come to know that there are uh, something else present in atoms along with shells, and those are called subshells and orbitals. So we will be studying that. So from the knowledge of from the knowledge of quantum mechanics, it has been proved that electron has a dual nature. It has a particle nature as well as it has a wave nature. And wave nature means that electrons are just not revolving around in a circular path, but while moving along a circular path, they are also moving in a wave pattern. They develop a wave pattern. And while developing a wave pattern, which are being found by X-ray studies and through quantum mechanics, it has been proved that there are 4 kinds of waves that can be observed. So this came to a new concept that atoms are not only made up of shells, but they are made up of subshells or orbitals. Subshells or orbitals are area in space where you can find electron. But before that, in O levels, you study that electron can be found in a circular path. In a circular path, the electron cloud is there, and that electron cloud makes an orbit. But now we come to know that along with the circular path, they have certain wave patterns. So that means circular path is called shell or orbit, and now we call it as principal quantum shell as well, principal quantum number. So if the shell number is 1, principal quantum number is also 1. If shell number is 2, then its principal quantum number is 2, and so on. So shell number and principal quantum number is same. So it can be denoted as n. So n can be 1, 2, 3, 4, or principal quantum number can be 1, 2, 3, or 4. But from the knowledge of modern physics, we come to know that when electron is revolving around the nucleus in almost an elliptical path or a circular path, they also have waves. And these waves can be of 4 types. These waves, the electron cloud has a wave nature. And these waves are very simple. One of the wave is spherical, which is denoted by S. The other is denoted by P, which is mean dumbbell shape. Then D subshell or D electron cloud means that it has double dumbbell, and F subshell is quite understudied still, and its structure is quite difficult to understand. So you don't need it for A levels. But S is a very simple, just like a football or a tennis ball. It's a sphere. Then P is just a dumbbell. Sphere has an electron cloud density in a sphere, and nucleus is in the center. But in dumbbell shape P subshell, the electron cloud is very small at node, and it has very large at proximities on the sides. Whereas D has 2 dumbbells, double dumbbells, so it has 2 nodes, but 2 nodes are are present at the same point, intersecting each other, and then there are 4 areas of electron clouds on the proximity. So every shell has subshells. Subshells are developed. Subshells are the area where we can find electron in a wave pattern. So how many subshells, how many kinds of waves pattern that can be taken by an electron in a shell? We have a concept about that, that it is equal to the number of shell. So subshells is equal to the number of shell or principal quantum number. So if we go to shell number 1, the first shell, the nearest to the nucleus, the lowest energy the shell, it has only one subshell. And it has been seen that only one subshell is spherical. So it means first shell has only S-shaped subshell. It cannot have P, D, or F. Then when we go to the second shell, which is further away from the nucleus, so its principal quantum number is 2. So it has two subshells. Now it has been seen that in two subshells, one is always S. One of them is always S, and the other is P then. So the second shell has 2S and 2P. So first shell has 1S, 1S. Then second shell has two kinds of electron cloud, S and P both. Then we name it as 2S and 2P. Then the third shell, according to the law, number of subshells is equal to shell number. Third shell should have 3 subshells. And when we have 3 subshells, then there is a liberty that the S subshell is present, P subshell is present, and then D subshell is also present. So D subshell was not present in the second shell, but now it is present in the third shell. The third shell has S, P, and D, and we denote them as 3S, 3P, and 3D. So writing the principal quantum number along with the subshell marks its presence, where it is located actually. 1s means that we are dealing with the electron in S subshell of first principal quantum number. When we say second principal quantum number has two subshells S and P, so we denote that as 2S and 2P. Then when we go to the third shell and we say that it has 3 subshells, it means that they have 3S, 3P, and 3D as well. Then in the fourth shell, there will be 4 subshells, 4S, 4P, and 4D. And then 4F is also there. But we will not be required to fill the 4F. We will be stopping till 4S or 4B, and we do not need to go to 4D even. So principal quantum shell number will tell us how many subshells are there. So first shell has only one S subshell. So electrons in first shell are revolving around the nucleus, and they have an electron cloud shape of spherical only. But when we go to the second shell, electrons are moving in a circular mean path, but along with that mean path, they will have two shapes of electron cloud, spherical as well as dumbbell. In third shell, which is a bigger shell, so there is a bigger capacity of electron wave nature. So we can see that there are 3 kinds of wave pattern of electron cloud, that is spherical, dumbbell, and double dumbbell as well, and then so on. Now, what is the energy level of these subshells? So generally, if we write it, so first shell is 1s, so it has 1s, that's the lowest energy, then 2s and 2p. So which of them has lower and higher energy? Then when we go to the third shell, we have 3 subshells, S, P, and D. Which of them has highest and lowest energies? And then when we go to the fourth subshell, which of them has the lowest and the highest energy? We cannot know about that till now. But to understand that, a scientist, a physicist of Bohr, gave us the energy levels of subshells in a shell. So if we go to the first shell, it has the only one S subshell, and as the principal quantum number one has the lowest energy, it is nearest to the nucleus. So 1s has the lowest energy. But when we go to shell number two, it has two kinds of wave nature of electrons, S and P, 2s and 2p. But which of them has lower energy? So according to the Aufbau principle, 2s has lower energy than 2p. But the energy difference is there. You see the diagram. 2s has lower energy, and then 2p is there slightly above 2s, higher in energy. And it means that 2p is slightly further away from the nucleus. You know that as you go away from the nucleus, the energy of the shells increases, so does the energy of the subshells increases. So 2s has slightly lower energy, it is towards the nucleus. 2p has slightly higher energy, it is slightly away from the nucleus. It is slightly away from the nucleus. So when we go to the third shell, it has 3s, 3p, and 3d, which is marked with the green color. And according to Aufbau principle, 3 has lower energy, 3p has higher energy, and then 3d is quite higher energy. But we see a new thing in this electron energy level we graph, that fourth shell has four subshells, 4s, 4p, 4d, and 4f. But fourth shell's 4s subshell has quite low energy. It has even lower than 3d. The energy of 4s has slightly lower energy than 3d. It's quite near to 3d, and that's why we will see that in transition elements they will flip as well. But uh, for normal elements it will not. So 4s has lower energy than 3d. So see how waves have expanded within a mean subshell. When electrons are taking the waves of wave nature or wave pathway, their energies are going way different within the shell. So if we see a shell, it is only four lines, n is equal to 1, n is equal to 2, 3, and 4. But when we see subshells, so they occupy a larger space within a shell. And so much so that when we go to the shell number 4, 4s is so lower in energy from the fourth shell that it has lower energy than 3d. So if we, now we see that 4s has lower energy than 3d. So 4s, this is where we will see that the trouble that we studied in potassium 19, that it has 288 and 1 electronic configuration and not 289, 2889. This model, this level of energies will tell us that the 2881 electronic configuration is perfectly correct. But this cannot be explained by previous models, which are called as Bohr's models or Rutherford model. But this new principal quantum mechanics model uh, gives us, or this subshell model will explain everything which was not covered by the previous models. So, what are the shapes of these orbitals? We have studied that uh, S has a spherical shape, P has a dumbbell shape, D has a double dumbbell shape, and then so on. But it has been further found that subshells are split further into orbitals. Okay, so it means that subshell has a wave nature, but these waves can be orientated in space in on different axes. These waves are spread on three-dimensional axes in a particular pattern. S subshell has a spherical shape, so it has a complete sphere which occupies the same space on x-axis, y-axis, and z-axis. So it cannot have any further kind of orientation. But it has been found that P subshell has three orientations in space: px, py, and pz. These are the three orientations that can be found in P subshell. So some of the electrons have a dumbbell shape, but they are lying on the x-axis. Only two can be there. Maximum electrons in an orbital can be two, not more than two. So if two electrons are there, or even one electron is there, as the electron is revolving on x-axis, then we call it as px. If the electron is revolving around in a dumbbell shape on y-axis, we call it as a py. And then there is a third possibility that electron is revolving around the nucleus in a pz pathway, pz electron cloud on the z-axis. So that can be there. D subshell has five orientations in space. Three of them are between the axes. It means that the dumbbells do not lie on the axis. They lie with their lobes lie between the axes, and two of them, which is dx square minus y square and dz square, their lobes lie on the axis. So let's see how these shapes of orbitals are there. So S subshell has a spherical structure, and it has only one orbital because sphere is equally distributed. The electron cloud of sphere is equally distributed on all the axes. So you cannot any different orientation for S subshell other than only one, that is to draw S sphere. So sphere has only one orientation and two electrons can be there. So S subshell is S orbital as well. It has only one orbital, it has only one orientation in space, and it's only sphere because the electron cloud is well distributed on all three directions. It is non-directional. The non-directional means if you cannot draw it separately on x-axis, y-axis, and z-axis, you can just draw a sphere, and that will occupy the three dimensions equally, all the dimensions equally, and there is only one possibility of drawing it. Then P subshell has a dumbbell shape, but dumbbell shape can be drawn on the axis in three different ways. On x-axis, on y-axis, on z-axis, you need to learn to draw these diagrams. Sphere, you don't need to draw the red color circle, but you need to draw a black and white simple two-dimensional diagram as shown on the right hand side of the picture. Then P subshells has to be drawn as shown on the right hand side of the page. If you are required to draw px, then its lobe should be on x-axis. If you are drawing a py, then its lobe should be on y-axis, as seen in the blue color diagram, and the same way it's drawn on in the black and white diagram. Then pz means that the electron cloud is located on z-axis. You need to draw pz as on the z-axis, and you may need me to draw all three together. So when you need to draw all three together, this has been drawn here, but you can draw it easily. It's not very difficult. You just draw the axes. You just draw the three axes. One is px, then py, and pz. Draw the axis first. Then what you need to draw is all three together. So if you draw one as py, then one as px, and then py, pz. Sorry, just need to draw a two-dimensional diagram. So you have drawn px, py, and pz all together on the same diagram. On x-axis, y-axis, and z-axis, you have drawn three p subshells, p orbitals together. But remember, one orbital cannot have more than two electrons, and that's why s subshell is s orbital and it has two electrons only. P subshell has total of 6 electrons, 2 in each px, py, and pz. And if we go back to the energy diagram, we have seen that P subshell has equal energy. You can see here P subshell, wherever P subshell is there, here or here or here, there is only single line over there. So P subshell doesn't have even further energy levels. It means that Px has energy equal to the energy of Py, and Py has energy equal to Pz. So all these three orbitals in a subshell, they have same energy. They do not occupy different energies. That's why as a collective, P subshell has only one energy level, and all these three subshells, three orbitals, will have the same energy, same energy केवल यहाँ present होंगे. They will not have different energies. So if the electrons are going into p subshell, so there will be a possibility that equal energies orbitals are available. So how electrons will go into that, we will study about that according to Pauli exclusion principle and Hund's rule to follow that. But all three orbitals of p subshell, px, py, pz, they have different orientations in space. So one is lying on x-axis, other is lying on y-axis, and the third is lying on z-axis. But their orientation does not change their energy and does not change their position from the nucleus. They have same position from the nucleus, same distance, and they have same energy. So 2p has three suborbitals, but they have equal energy. Same case with 3d. 3d has a double dumbbell shape, and double dumbbell shape electron cloud can have 5 orientations, so they have 5 orbitals. But all 5 orbitals, dxy, dxz, dyz, dx minus y square, dz square, all of them have equal energies. So orbitals in a subshell will have equal energies. So this is p orbital. You need to draw a simple diagram of p orbital. Then d orbital has a double dumbbell shape. So how to draw a double dumbbell? So you just need to draw these axes, x-axis, y-axis, and z-axis. So if I draw a double dumbbell, so if I draw between the axes, you see I'm not drawing on the lines of the axis, I'm drawing between the axes. So if I draw one of the lobe is here and the other lobe is here, this is a diagram of your D subshell. So if I write it like this, it is x-axis, this is y-axis, and this is z-axis. If z-axis can be drawn with a dotted lines, it's a better way to draw it. So this shows a p. This shows a d orbital whose lobes are located between x and y axis. So we just label it as dxy, and dxy can be labeled as dxy. X and y will be its subscript, it should be written below uh, dxy. F subshell have a very difficult shape to understand, so we don't know about that. Now comes the electronic configuration. Let's first decide what is the energy level of these subshells. So 1s, you need to either rote learn it, or you just need to draw this diagram and draw diagonal arrows pointing downward. Then you will be able to know which has the lowest energy. I write first, you write 1s, then you write second shell as 2s 2p, then third shell as 3s 3p and 3d, then fourth shell as 4s 4p and 4d and 4f, and then fifth shell is good enough to draw it. We don't need any further. 5s 5p 5d and 5f. Then you take a scale and you start drawing diagonal parallel lines pointing downward, and then you start from the tail of the first arrow at the top from 1s and start following the arrow to tail, arrow to tail, arrow to tail. So 1s to 2p, 1s to 2s, then 2s to 2p, then 3s, then 3s to 3p, and 4s, and from 4s then you go to 3d, 4p, and 5s. So this is the Aufbau principle. According to Aufbau, electrons are filled in subshells and orbitals according to the increasing energy level. So the electrons will go to the lowest energy subshell first, then to the higher energy subshell, and then to the further higher energy subshell. So the lowest energy subshell is 1s, then 2s, then 2p, then 3s, then 3p, 4s is low energy than 3d, and then 3d has lower energy than 4p, and then 5s, and then 4d, 5p, and 6s. So if you can draw this diagram to, or either you rote learn the pattern 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, that's good enough. There's another way of remembering that by mnemonics, and that is school, 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 school. That mnemonics is, you can easily remember by this mnemonics: school, comma, school, then public school, then repeat it again, public school, then divisional public school, then public, divisional public school, and then again divisional public school. If you take their first alphabets, you will see that the same pattern is followed. You just give numbers to it. So if I give numbers to it, so if I write 1 here, 2 with S, then 3 with S, just number the S first, then 4 with S, then 5 with S, and then 6 with S. Then you start numbering for P, and you know P subshell is not in the first shell, so its numbering can start from 2. So you write 2, then 3, then 4, and then 5. And you know D subshell starts from the third shell. It does not it is not present in P and first and second shell, which are smaller shells. So D cannot be present there. So start numbering from P, 3, and then 4. You will see that you have same arrangement, same pattern. So if I just repeat it for you, sorry, 1s, 2s, 2p, 3s, 3p, 4s, 3p, 4s, then 3d. You see, so same pattern is there that is being observed. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s. So if you just write the mnemonics and you start numbering for s with 1 and then p with 2 and d with 3, and you just keep numbering them with from increase smaller to increasing number, you will have the same pattern as Oppo. So this is the energy level of subshells according to Aufbau, and electrons are filled from the lower energy to the highest energy. Now, if you fill electrons in a subshells pattern, so there are different ways to represent it. One way is to represent by using arrows, and using arrows on a graph, or just by drawing a parallel arrangement. This can be drawn as a graph as well. So if we have boxes and a arrow diagram, so electron has spinning on its axis. So, and we know that half of them are spinning on clockwise direction and half of them are spinning on anti-clockwise direction. So if we take electron as a particle and it is spinning on its axis, this is your electron, and it is, suppose it is spinning clockwise. So the other electron in the same orbital will be revolving around the nucleus in anti-clockwise. That is the Hund's rule, that no two electrons can have same spin in an orbital. So electron in an orbital, the two electrons can be present, and if the two electrons are present, one of them is clockwise and the other has an anti-clockwise spin. So that's why you see that these arrows are now double-headed, are single-headed, and they are opposite. They are opposite. One is directed upward and the other is directed downward. But if an orbital has only one electron, so you just need to draw the upward direction. You don't need to draw one upward, one downward, one. So you just need all of them in the same spin. So you need to draw the electrons. If you see here, there are three electrons and they have same spin. This is also called Hund rule. If the same energy orbitals are available, such as P subshell has 2px, 2py, and 2pz, and you have three electrons there, you need to put them in separate orbitals and not in the same orbital, and have same spin. According to Hund's rule, this will give more stability, because if electrons will go to different orbitals and have same spin, they will have lesser repulsion and the atom will be more stable. Rather than putting two electrons, if suppose for carbon, if suppose for carbon, what I do is that for this orbital, this subshell, I अगर आप ऐसे ड्रॉ कर देते हो कि ये इसके थ्री पार्ट्स हैं, and you draw two electrons here and then just draw one electron here, so this is wrong. Okay, this is totally wrong. Is even this is not there. इसको ठीक कर लेते हैं. Let's draw it neatly. If I place electrons in the same subshell like this is totally wrong, because according to the stability of atom, if two electrons are to be occupied or three electrons are to be occupied in p subshell, then p subshell has three same equal energy orbitals. So it is preferred that electrons will go to the different orbitals and have same spin that will have lower repulsion than to go to the same orbital and have paired spin. But in case of, if you see, in case of oxygen, there you cannot do anything because it has four electrons to be accommodated in p subshell. But even then, you see that when first we put three electrons separately in 2px, 2py, and 2pz, but then the fourth electron has to be present in the 2px first. So then 2px will have a paired spin, opposite spin, to reduce the repulsion. Then in case of